coming this way, or? Sure. No problem. All right. So this is the last of our full days of talks. We'll have another talk from Shahar tomorrow morning to start off the hackathon. Our closing keynote from Liran Zvibel. Okay. Everybody probably will have heard of Weka.io. Liran's the CEO and the co-founder. And if you follow their Twitter feed, which if you're not, you should, they've been generating a lot of buzz lately for their file system, which is written in D. And today we're going to get an experience report from that. Liran?
All right, thank you. So just to give you some context, you're not going to learn anything new about D from my talk. The reason I want to give this talk is so other people around the world, probably not the ones in this room, could point their pointy-haired bosses to my talk and say, hey, there is this crazy other pointy-haired boss in the world. He has bet on the 5 years ago, and 5 years later it has paid off. So when we go to our agenda, we'll start with some background and history. Then we will end up saying what we're doing, because the last times I was talking, we were actually still under stealth. So we were talking about a lot of problems we were having, but we actually didn't tell you what we were doing. And then talk a bit about how the project looks, and I'll give a preview to Shahar's tomorrow Mecca unveiling. So some history. So if you probably remember, and there are lots of familiar faces here, this is my 4th DConf. I've first came and gave my first talk in 2015 in Orem, Utah, which was the last one in the States. And we have been repeatedly coming over here, so we're doing D for 5 years, so I think that we're stuck with D and you're stuck with us. So get used to it. So I want to give a bit of a background, because probably our first few times weren't as influential, and you didn't know, you should have listened. So I'm going to give you some background. So this whole thing started with a tweet on Twitter. We actually formed Weka.io end of 2013. We got the first money January 2014, and then we started working on infrastructure for the project, and the infrastructure was basically trying to compile C++ into Python, because we wanted the data plan to run in C++, because it has to be fast and low latency and high performance, but no one in his sane mind would run very complex control flow in C++, because you'd end up getting crazy. That's our previous experiences, at least. So while we were doing it, I was taking a break, reading Twitter, the true story. So this is not like rewriting, this actually happened. And then I saw that Ken Beck was writing about a Flint for C++, and I said, hey, we're going to work on our new infrastructure. Let's make sure it supports that Flint from early on, because we were doing a C++ project. And then I clicked on the link, and now Ken Beck has a lot of respect, and I see that Flint was created by Andrei Alexandretsko, which I've said it repeatedly. For me, since I started doing C++ in the late 90s, and reading the C++ user journal in the Dr. Dobbs, and obviously the modern C++ design, which changed everything. For me, Andrei was basically a god, or at least someone that would have been the equivalent, and I said, all right, so he wrote this Flint to help us with our C++ project, but he actually did it in a new language for us called D. So we knew Andrei, so it started with Kent Beck, which is a huge name. It continued to Andrei, which is a huge name. We downloaded the D programming language book, which basically back then was the only real documentation for the library. We started playing around, and, well, famous last words. So we ended up being here. So instead of using the Flint to make sure our Python and C++ abomination was safe, we've actually decided to divert the whole project to be the only, because we could write high-level control flow code, which will end up being very high performance. And I can tell you 5 years later, and even it's easier to write high-performance code in D that will actually be higher performance than what you can easily get with C++. Then, about a year later, we thought we were going to hit a wall. And the reason we thought we would be hitting a wall is that the only compiler that could compile our code was DMD. GDC compiled, but it didn't run, and LDC didn't compile. So the compiler would just repeatedly crash at very different places, and we basically sort of, we thought we've wasted a year, and as a Hail Mary move, I said, I'd go to DConf, give a talk. I went it all the way to Utah, and then, luckily, as we'll see later, David Nedlinger, which sadly isn't here, came to me after the talk and said, it doesn't make sense. LDC must work. He started LDC, so it will be a good optimizing compiler, and it must work. He actually went through, I think, about 3 segfaults during DConf, and then we continued working, and about a month later, we got an optimizing compiler compiling our code. So this Hail Mary move actually worked, and coming to DConf 15 was a very, very smart move on our side, because we got a compiler. Then, the following year, we actually came to Berlin to the 16 LDC to talk about our progress. And then it wasn't just we hit the wall, we've had more symbol length issues, we've had compile time, we've had project structure, but basically we had a compiler that worked. I think we've had Johan by that time, which replaced David and is still with us, so I'm thankful for that. And we've converted our problems from things that basically were solve it or switch to smaller and smaller and smaller problems, and I'm proud to say that we're quite happy with what we currently have. So we've had David Nedlinger, we started working on the optimizations, and we still have some code size and complexity issues, but we are, I think, very effectively going through them and solving them, and again, a huge thank you to Johan. Then, last year, actually I didn't end up giving a talk because we tried to get Andrei to come to Israel and get better adoption of the D language in Israel, so I spent my time arranging Andrei's trip to Israel. which got me to learn introspection as deep as it could. So I heard Andrei's introspection talk on DConf, and then 5 more times, I think, during the following week. So I could basically repeat it in my sleep. So you can see that we went to Tel Aviv University, went to the Technion. The middle one is in the Weka IO offices. We've had a very successful talk at the Google campus with almost 200 people showing up to the talk. People were standing in the back, so there were like 160 seats, and people were standing in the back. It was like a rock star came to talk about programming languages, which was very, very impressive. So a short summary to finish the initial part of these talk. What we are doing, we are creating, as we're going to see later, the highest performance file system. And if we want to create the highest performance file system, algorithms aren't enough, the implementation has to match it. And the D language, which is an extremely high-performant programming language on the one hand, but a language that allows us to handle complexity on the other hand, is crucial to our success. I think I can safely say that no other programming language would have allowed us to, as you said, generate the current Twitter feed as we generate and get the amount of interest we generate at the very high-profile customers and partners that we're working with that we're going to see later, because introspection, compile time execution, meta-programming, generic programming, it doesn't matter how you call it, the ability to offset a lot of the decision of what usually happens in runtime to the compile time, and then you have the runtime do exactly what it needs, is a huge thing. And having it actually happen in a language that you can read is amazing. Because if you've been doing large C++ projects, I would assume you've had this case. You wrote some C++ module a year ago. It made perfect sense. It all fit. Then you go back to it. You try to read your own work. And it's extremely difficult. And it doesn't happen with D. Because D has the sort of brevity that lets you focus on the things that you should care about. And while you're focusing on the thing that you should care about, it's a lot easier to get the functionality on the one hand and the performance on the other hand. The thing that we care about, and I think our problem is that there aren't many other large projects so other people would care about, are support for large projects. So better handling huge imports tree, making sure that compiles finish earlier, taking care of executable sizes. So there are a lot of things that could have still be improved, but no language is perfect, and I don't think that C++ has handled scaling project much better. So C++ projects still take hours to compile. It's not a good benchmark, but that's just life. So this is actually my first DConf talk after we're coming out of stealth. So I'm going to go through some Weka IO slides, so when we tell you what we're doing, you will actually understand what we're doing, and I will try to put it in some perspective. So we've created the fastest file system, and it's easy to say that we're the fastest file system because on each public benchmark we are the fastest. So it's not just us saying it's the current fact. And also what we're showing that we are infinitely scalable. So we show customers that they double the resource, they get double the performance. And the gist of it is that we allow a lot of people to take problems that are I/O bound because they couldn't get enough I/O from the current solutions and make them CPU bound. So storage is basically boring. You just need to read what you've previously written. The problem with storage is in many, many cases, it's just not fast enough. So there are many applications that depend on storage, and in the file system world, it's shareable storage, and then you would have an application that could run faster, but it doesn't because you're waiting for I/O. What we're doing, we're making sure our customers don't wait for I/O. So the one thing I think we were able to share previously is our people, the kind of talent. So we are very experienced. We have done these projects previously. We are hiring mostly people that have done it previously. So if you didn't do it for 20 years, it's very difficult to innovate in the same way that we do. We already have quite a lot of partners. So on Monday, Hewlett Packard Enterprise is going to start reselling Weka IO on their servers, especially around technical compute, machine learning, AI applications. We're in very close ties with both Intel and Mellanox. We are an AWS advanced partner, and also we have Supermicro and Penguin Computer reselling us on their servers. So in a very short while, since we have become public, when we started saying and telling our story, very reputable vendors starting testing us and realized that indeed we solve a real problem for them. And the takeaway for you, the D community, is that there is a large D project that generates a lot of interest. So I don't think that anyone from HPE really cares that we've implemented it in D, but that's the fact. It's implemented in D. And now when we go as a community and talk about outreaching and bringing in new projects, we can use it and we can leverage it and say, hey, the machine learning solution that HPE or that AWS pushes actually leverages D. We did get some awards recently. So just last week, we got the Gartner Gold Vendor Awards, the Storage Magazine Product of the Year, and quite a lot. So it shows that we do generate real, genuine interest. We have some premium customers. I was almost sure I will be able to tell you the name of the customer on the top right, but it just didn't, the legal details didn't finalize in time. But we're actually in production in 2 autonomous driving projects. And the reason autonomous driving projects are interesting, or machine learning projects are interesting, is that there are a huge number of projects that are coming up that are replacing CPUs with GPUs. And basically what these customers see is that when they were using CPUs, they were compute bound. They just couldn't crush enough through the large neural net models they had to build, the deep neural networks they had to build. But when they're moving to GPUs, they have a lot more compute, and now their problem turns into they're I/O bound. And actually, our biggest competitor is proud that they're able to reduce epoch time. Epoch time is the time it takes for a single training cycle to finish from a month to a week. And then they say in their talks, hey, we take you from 12 cycles a year to 52 cycles a year. We're currently in production in 2 of the most ambitious autonomous driving projects in California, one for cars, one for trucks. I met, the day after that vendor came out with these claims, I was at one of these customers and asked him, hey, what is your epoch with Weka? And they said, an hour. So there is one thing to say, hey, I'm taking you from 12 cycles a year to 52 cycles a year to saying, hey, what you may be doing with the competition in the year, you're doing with Weka IO in less than 3 days. So these are the breakthroughs that the machine learning world is really looking for. And once we are able to start talking about these things and have these customers start evangelizing their solutions and show that they reach results a lot faster, we'll actually be able to show that our adoption will increase further and further. Talking about genomic processing, we're working with TGen. They're a genomic institute in Phoenix, Arizona. And what we've showed them is that they can linearly scale their compute. So no other storage solution that they've tested allowed them to keep being CPU bound. And we showed them that with Weka IO, it doesn't matter how many servers they add, if they have one server finish in X amount of time, 10 servers will do 10 amount of work in that time. And this is huge, because what's going now with these genomic kind of workloads is that if you can run more computations, you become smarter. So you understand more about genomes, or you can look at more genomes, and you get much more results. San Diego Supercomputing Center has run us also with life science workloads. They compared us to an open source solution called Luster. We've achieved great results. One of the results, we actually finished 100 times faster than what they were running on Luster. So we're not talking about 15% faster, we're not talking about 50% faster, we're talking about 100 times faster. So when we're able to provide these kind of performance increases, these are huge, and the ability to provide these kind of performance improvements is that we care about the latency of every single thing we're doing. So, by the way, we'll get to it later, the vendor that moved it from a month to a week, talks about how they're using FPGAs and no one can win because they have such smart FPGAs. We just use Intel CPUs. So, but we use a good way of leveraging these Intel CPUs. This is part of our recent Twitter feed, so you can see that this is where HP announced to the market that they're going to use us for their machine learning. This is where NVIDIA, that they're making the GPUs that you put in these GPU field servers, said, hey, with Weka IO you can actually leverage our GPUs. The right one is where we've achieved the fastest file system for the public spec SFS result. This is another analyst talking about this kind of workload. So we are able indeed to leverage quite a lot of interest in the recent amount of time where we're talking about what we're doing. I'll give you a very quick overview of what our solution is, because a lot of people don't really understand storage. So traditionally, when people wanted to get high performance, which usually translate to low latency storage, they couldn't use shareable storage. They used an all-flash array or a SAN, which is basically saying, hey, instead of connecting to a local drive, I'm going to use a network drive that is faster because it uses more spindle or it uses flash. But as I said, it's not shared. Then you have the shared solutions, and if you wanted them to be somewhat fast, or not very slow, you use the all-flash file systems. Then you can use scale-out NAS or the scale-out parallel NAS, but the problem that the NAS solutions don't scale, so you're reverting to an object storage solution that scales but has even worse performance. What we have at Weka IO, we have a file system with lower latency for where people care about low latency, 4K IOs on the one hand, but we scale even bigger than most of the object storages on the other hand, and we broke all the metadata limitations. So you can have trillions of files in a file system, you can have billions of files in a directory, and if a directory has billions of files, it works as well as a directory with 1,000 files. So you don't have to have these artificial limitations. Hey, I take the first letter of the patient, I create a directory for it, and then finding things is difficult. You're laughing. People do it. For us, you think, hey, how does it make sense to store the data? How does it make sense to represent the data? You use that form, and you get the best performance. And you just keep doing what makes sense. Very quickly, we support bare metal, we support hypervisor, we support Docker or containers, and we run either on-prem or the public cloud. Our file system is fully coherent POSIX, so you don't have any limitations. If your program runs with ext4, it will run with Weka FS. The protection is distributed coding. You can think of Reed-Solomon, but we don't have the performance disadvantages of Reed-Solomon. So you can choose +2 or +4 protection, and you can have wide stripes, so it's very efficient. We even have end-to-end data protection, so we provide higher integrity than the solution that have less performance. We have snapshot steering, a lot of the advanced features, and this is again where D comes into play. If we had to use the initial solution that we started with between Python and C++ or C++ only, or any other solution, coming up with such advanced features would have been a lot more difficult for us. So this is another place where D really helps us. And we're very flexible, so we support either InfiniBand, which is very common in the high-performance computing world, or Ethernet. We run in a form that is either dedicated servers for the storage, or we can actually share the same servers with the compute. And we basically care about applications that care about performance. If you don't care about performance, you will probably not pick us. You'll choose to go with a more established vendor because no one chooses to work with a new vendor unless they have to. But if you're doing genomics, if you're doing machine learning, if you're in the finance world, if you're manufacturing, media and entertainment, I didn't even talk about DreamWorks because I had more sexy logos to discuss there. And DevOps, all these applications actually care about what we do. A big secret that we can actually do what we do is that we make network hops or pushing computation to another computer irrelevant. So a lot of people have a local file system which is the fastest, and they say once you move to a shared file system, it breaks. The reason it breaks is that they end up using the Linux kernel TCP/IP and the Linux kernel scheduling and the Linux kernel memory management. But all of these things aren't geared to low latency. And if what you're doing is running tons of small operations, you don't care that each one of these small operations takes slightly higher latency, but when each logical operation is basically the accumulation of maybe dozens of these or 100 of these, it makes a huge difference. So this shows that how long it actually takes for the hardware to do things. When you look at NVMe SSD, writing takes about 30 microseconds. It doesn't matter what vendor you buy from, this physics. Reading takes about 100 microseconds. But if you look at 100 gig networking, either EDR InfiniBand or 100 gig Ethernet, moving a page actually takes less than half a microsecond. If you run the math, 0.36 microsecond, which is nothing. So making sure these latencies don't really matter for us, we're able to actually take large IOs and instead of running them over a single SSD in a serial way, parallelize them on many, many SSDs. So if you're just running 4K IOs, you're going to get the same kind of latency you would get with a local file system. But if you run 1 meg IOs, you're able to leverage several SSDs, and they come together. Yes?
I just wanted to add that when we do single write operations, we often do more than one network hop. So the latencies Liran is quoting is not from the machine doing the write to the machine with the disk. There's at least one other hop in the middle, and the latencies Liran is quoting is after this extra hop.
So this actually talks about our runtime, and part of what you see here, Shachar will talk about tomorrow when we open source it. We actually don't run in the Linux kernel. What we're doing, we take away full cores, we take away full pages in terms of huge pages that we manage completely, and then using our reactor with fibers, we run our own memory management. By the way, we have different kind of pools that we will also open source, similar to the pools that were allocators that were discussed earlier. We have very efficient ways of scheduling our fibers. We have a very efficient networking stack, and we have a very efficient I/O stack. So we take control over the whole SSDs, the whole NVMe. So if you run LSPCI, you will obviously see them on the bus. But if you run the Linux LSBLK, we actually take it away from the Linux. So we're using some virtualization techniques to basically share the hardware with Linux, but don't use Linux for anything except for running a VFS driver that provides the file system. So we only suffer the Linux latency issues when we're implementing the APIs that Linux forces us to implement. And the gist of it is that we're running an RTOS written in D on the same server alongside the Linux kernel. And we're using Intel virtualization techniques to basically share the same cores, or not the same core, we take full cores, share the same CPUs, and run everything ourselves alongside, providing very, very low latencies. And if we couldn't manage the performance of what we're doing thanks to D, it wouldn't have been possible. These are some performance numbers. The orange one is a competitor. If you're in storage, you would recognize who is Orange. As I said, they take pride in building up appliances with FPGAs, explaining why no one else could be faster. And these are actually results from single servers. We would scale to as many servers. And these numbers came from actual bake-off at a real customer on their environment. So you can see that for 4 meg IOs, we were getting about 7 gigabytes of throughput. Obviously, this was with a 100 gigabit networking device because we were able to transfer 7 gigabytes per second. We're actually showing at NVIDIA and others that out of 100 gig, we get 11 gigabytes, which is the theoretical limit of what you can do. But they only were able to use 7. We were able to get a lot more IOs, and then these guys were saying, hey, but we're an appliance, they're a distributed file system, try running some metadata operations. You're going to see that with the metadata, they'll be way slower than us because that's how distributed file systems work. So they started with them. They ran fine from a single host throughout the file system. It was a big one. And that vendor finished in 6.5 hours. Then they told them, hey, the Weka will take a week. That was their experience with comparable solutions. They ran it on us, and we finished in just under 2 hours. Listing a huge directory took almost a minute for the competitor, and we finished in just 10 seconds. And all these things are possible because we're able to get great performance out of standard CPUs thanks to D. This is the public spec SFS benchmarking. I'm only showing the first 3 results because around here there are many, many others. So going over 200 is an impressive number. So most other graphs are just around the beginning of this graph. And we are comparing to NetApp's biggest box and IBM GPFS with NVMe drives biggest box, or the box that they were able to do. And we were actually running with about 2/3 of the resource than either IBM or NetApp. And the x-axis is the number of concurrent clients. So going further is better. The y-axis is latency. Obviously, no one likes latency, so lower is better. And you can see that we were able to get more than twice the concurrent clients, and our latency increased much better. Also, IBM was cheating here. They were actually, if you look at these latencies, and if you read the report, they actually admit 1/3 of the first IOs, they were actually caching in memory. And since it's a primary storage benchmark, memory caching doesn't make sense. You can see that both NetApp and us started with flash latencies. So we were actually running a lot more IOs to the NVMe devices than what IBM had. And once they started hitting the storage devices, their latency started going way, way higher. So some statistics. So we said it's a big project. Let's quantify it. These are things, I took all these measures on the plane this morning, so they're very up to date. We have about 1,200 D files and about 280 lines of code. When I looked at my 2016 talk 2 years ago, and also we had about probably half the developers, we had 200K lines of code. So we've doubled the length of the project. We've doubled our resource of people churning on code, but we didn't actually double the code base. And we've talked about it with Andre when he was in Israel, and we've come to the realization that when the programming language is so strong and so effective, and the ability to run a lot of our decisions in compile time and really do leverage generic or meta programming, we can add a lot more functionality without adding a lot more code, which makes the whole project much more manageable. And then I tried to quantify how much of these do we have. So out of that amount of lines of code, we have 2K static ifs. But by the way, this is just static, a single space and if. I didn't do anything complex. I didn't run it through a lexer or a parser. So there may be more cases, but even this basic thing is quite a high number. Only recently there is static for each, so there are already 20 of these in the code. I'm sure we have tons of for each, which is in fact static, but I have no way for grep to easily tell me how many.
Actually, we have a construct that it's iota with uppercase that we gave it a number and it returned a tuple for that number, so you could for each about it, and it would become a static for each without the language support. So we were using static for each before the language had it formally.
That will probably still be faster than static for each, depending on the number.
Yeah, by the way, any suggestion on getting our compiles faster would be highly appreciated. There is nothing engineers want more than faster compiles. We have 115 mixing templates. We have tons of other templates, but as I said, I was doing it on the plane this morning, so I didn't really dig in to see what's going on there. And another thing I did, I tried to come up with a grep command that finds all the exclamation marks that aren't negations. I cannot promise this is the absolute truth, but I found more than 27K cases where I randomly stopped in the middle of the grep and the whole page made sense. So we have quite a lot of explicit instantiations. Obviously, many cases don't need the exclamation mark. So we're using all the static system quite significantly. We have tons of CTFE code, and in 30 places, people actually made sure that what they're doing ends up being CTFE. I couldn't easily quantify how much, but one thing is very strong. We are trying to leverage as much of the compile time and static analysis feature of the language as we can, because this is our unfair advantage. So when we're using D, we're trying to do things that other people cannot, and this is basically the strongest weapon of D. Some cool anecdote. This is as technical as this talk will get, so I'm sorry, but you've had like 3 days of technical inferno and people coming up with cool tricks. And this is actually similar to the layout discussions you've had previously, just we don't care about qualifiers. What we care is that we push quite a lot of things through the network. Actually, if we have 2 cores running on the same server, they never talk through memory, because this would not let us scale. So we don't care whether 2 cores sit on the same server or sit on different servers. They always run RPC through the network. But then we have to support seamless upgrades. So it means that in many cases, we have portions of the clusters running different versions, and we have to make sure that the RPCs will still work. Or if they don't, we have at compile time to know, hey, we have to come up with a special case for the release and the N-1 release so it would talk. So we've already talked about our IDL-less RPC, which was impressive, I think, even in 15 when I came over. But now we have IDL-less RPC that verifies that you can actually upgrade from one version of the system using RPC to another version of the system using RPC, basically looking at the functions, but mangling is not enough, because let's say you're passing struct A may have changed. But struct A may have not changed. It may have a nested other struct that has a nested other struct, and that struct changed. So we're actually using recursive introspection to make sure that when we send an RPC, it will always work between every 2 versions. And I cannot think of any other language that will allow us to have an IDL-less RPC at high performance and this level of safety. So we are able to leverage D to not only be high performance, but to also be safe. I don't have a lot of time, so I'm not going to dig very deep into this. But our biggest pain point is because we cannot use GC, because GC takes forever. GC easily can take milliseconds, and for us, milliseconds is forever. We cannot really use delegates, because in many cases, even if you tell them that they're statically scoped, that they're scope delegates, the compiler cannot be convinced and would allocate them with the GC. And since we have no ways of convincing the compiler in all cases, it's a very strong feature that unfortunately we cannot use, and we actually have some tools in Weka, our library, to solve things without delegates, but if we could win them back, it would be a huge thing for us. So just summarizing this point, we care about safety first, because storage has to be stable. It has to always work. If you wrote something, you must be able to read it. Then we care about performance. So performance without safety is meaningless. But then from the programming language perspective, we care about brevity and the ability to manage complexity. If I can be a bit opinionated, because Andre said it's going to be called keynote, so I have to have one opinion. So my opinion for this talk is that D needs to improve the first 5 minutes. So we have friends that we're trying to force D on them. And their problem is that onboarding them is a huge effort. So unless you're already in love with D, it doesn't look compelling enough. And I think that as a community, this is a very important thing for us to improve. Because the fact that we fell in love with D, and it's a great tool for our work, doesn't unfortunately help us to get other people there. So I'm going to just very briefly mention, you're going to get Shachar a full hour on it tomorrow, but we are taking a lot of our infrastructure that we've spent the last almost 5 years building, and we're open sourcing it. So we call it Mecca. It's a play on the name Weka. We have a lot of our internal tools have some letters and Eka at the end. So the open source is Mecca. We've actually started separating infrastructure from the project quite a long time ago, August 16. So there was a quite famous campaign going on. So the first commit was make Weka's infrastructure great again. Hopefully it will work for us better than the other campaign. It actually moved to its own repository about a year ago, and shortly thereafter we've put a full-time resource, which is Shachar, on it. So we're actually, for a startup, it's a big commitment. You should view it as our basically operating system implementation. What we don't put there is our networking, because it doesn't make sense in other people's context, and also the actual I/O stack. So, but anything, since most of you don't care about low-level managing NVMe devices and pushing things over InfiniBand, I think it will actually be very useful to a lot of the projects that care about safety and performance. It has 3 major components: Reactor, which is basically a scheduler, lib, that allows us to run a lot of our no-GC functions, because Phobos assumes GC too much. We cannot actually use most of Phobos, and containers, which are our containers that don't allocate. It has what we call pools, which are other people's minds of allocators. So in storage, everything is statically allocated, so the program starts with a pool of resource, and you may only use from that resource. If you think about allocators from that point of view, hey, I'm limiting myself to the amount of resource that I'm running, you're basically running a pool. We have arrays, queues, we have tons of different kind of queues because they have different functions. So I'm sure that Shachar will have a lot of fun tomorrow explaining all of these, but the gist of it, if you care about no-GC, if you care about safety, if you care about performance, we're going to donate quite a lot of components that make a lot of sense in that regard back to the community. All right, But it's great. So we will have released yesterday. Thank you. I have about a minute to spare, so if you have questions, I'll be happy to take them.
And we can go longer than a minute if we need to.
Well, they all want to go have their beers, so...
Yeah. You mentioned compile times. Can you disclose how short or long they are? Compile times.
So if you're just running a small incremental build, it takes minutes. But unfortunately, when we run a release build of everything, and the release build actually runs LTO and all of the other things, it takes hours. I'm sure that Johan can tell you better figures than me, how long it really takes. But it's not something you stare at.
In fact, I don't know. Are you using LTO at the moment or not?
So
Okay, at least I made LTO work, I'm sure. And I wonder, I'm not sure if you use thin LTO yet, which would be the parallelizable.
No.
Okay,
I don't
so
think we used thin LTO. We just let the LLVM gets everything and think of it in
yeah, so I would expect
file.
big gains from using thin LTO because it's parallelizable. And you guys usually compile with like 32 cores at the same time, so.
Though I'm not sure that the link time is actually what's taking most of the time. All right.
Can you tell something about the future? Have you new features in mind, or what's the plan for the file system?
Features for the product?
Yes?
No. But we obviously have plans, so we're not going to fire everyone.
Stefan?
Just about the compile times, for everything that's happening in the front end, so templates and CTFE, I can actually give you numbers that tell you which parts of the source code are responsible for what amount of compile time.
This should probably prove to be very effective for us because we are repeatedly trying. When I say we, I don't actually do any of this, but our engineering is spend a lot of time trying to pinpoint where we are wasting time and optimizing either around our code or around LDC.
Yeah, so a lot of people have said that one of the biggest killer features of D is the unit tests. I was wondering if you could say anything about how you use unit tests or if you're using your own thing.
So we used the unit test feature. We have a different runtime for the unit test because sometimes we want to fuzz specific sections longer. So we have the default mode where all the unit tests run, but also when they run, we get the reporting. I think that Attila showed similar system, one of two.
It's actually part of
decons
Weka. We have actually released that part.
Huh? See, better than me.
Do you have a recommended software stack for the applications? Because you mentioned machine learning and all the stuff, so do you have something that you recommend for the people that buy your products?
I think that it looks like the more advanced customers are leaning toward containers, but it's not our place to to have opinions on that. We just need to make sure that no matter what you choose, it works well. But I think that looking at our customers from their IT infrastructure perspective, the impressive ones are moving into orchestrating things into containers and between Kubernetes or Mesos or these other frameworks.
Okay, thanks.
Do you have any in-house developer tools developed for the development process, or are you using just the open source ones?
Sorry, what? Internal?
Do you have any in-house developed developer tools to help you in the development process, or are you just using the existing ones?
So are you asking about the IDEs or the way?
Yes, the IDs and other tools.
If you think you can hire developers and tell them what IDE they can use, there's no way. So each developer uses their own solution. It's a lot better than the one that sits next to him. And obviously, or Emacs, or Eclipse. So we have everything. And we do have some tools that lets you run cross-referencing and introspection and these completion, so based on, I think, DCD? No, but I think for a while, the standard one didn't really work on our code.
But
so.
the thing is, one of our employees is Idan Aryeh, who wrote the Vim plugin to DCD. So it was very convenient when I ran into problems. It just, hey, Dan, I need your help.
Yeah, so we make sure that no matter what IDE you're using, you will get good support. And even though our developers could think that you're an idiot for choosing that IDE, they will help you hook it into the rest of the infrastructure. That's life. You couldn't I've once heard that another thing. People would say, why there are so many libraries doing virtually the same thing. Also with us, with Meka, there are other projects around that are similar. And the gist of it, which is similar, is that you cannot tell a developer there is already a library that is similar to how you cannot tell a poet there is already a song about love. So it's not their song.
Liran, thank you very much for an interesting talk and for your contribution to the community. I wonder, for the benefit of others, what advice would you give to, for example, you talked about your friends who were trying to persuade them to adopt D. What advice would you give to relatively early adopters, relatively early commercial adopters of D, based upon the kind of lessons that you've learned from going through this sort of process, which isn't a straight line up, I guess? Some things are probably unique to you in your domain, but there are probably maybe some general insights that you have from kind of...
So early adopters, when they come to
commercial adopters, yeah. Commercial adopters.
For when they choose to run their next big project on D.
Or the next medium project, whatever.
Yes. Don't give up. It's worth your while. That's basically the reason I'm here. So the problem with D, which is basically what I said earlier, is that onboarding is horrible. We were confident when we started that this is where we want to go, and we just banged our head at it until it worked for us, and we're very happy now. So I think that onboarding to D is harder than it would be in a perfect world. But once you've went through, it's not just a learning curve, it's a toolset curve. It's this whole process of making it work for your kingdom. You're actually going to reap tons of rewards. So the best advice is keep banging your head at the problem. It's going to be worth your while.
So apparently designing or like implementing a file system that actually doesn't have a single point of failure is tricky. How did you convince all these like high-profile companies you're not going to lose their data?
So that's not the context of this talk, but we've actually run design reviews with the Smart Analyst, Gartner, for example, or the experts at Hewlett-Packard Enterprise or at AWS, and we were able, through long weeks of questionings and answering, to prove them that indeed we've architected a system that does it. It's I cannot explain it within a sentence, but it takes a lot of experience and a lot of dedication and caring for the detail. QA is a huge part of it. You can ask Johan what he has to go through to upgrade a compiler version. So that's the reason we're always a bit behind. Making sure you're stable is very important, and it's important from the architecture, through the algorithms, through the implementation, through the QA, and no, it's not a single trick pony. You just have to do a lot of very, very, very hard steps throughout the way. So just work hard for enough time, it will happen.
All right. Thank you very much, Liran. Okay, and that concludes our 3 full days of talk at DConf 2018. Tomorrow we have the hackathon. We have breakfast at 9. At 10 o'clock we have Shahar's presentation, and then we start the hackathon. We still have the room tonight until 10 p.m., so you can hang out here and have your beer time or whatever. And I want to beg your indulgence for just a little while longer. We want to get a group photo, which we usually do every year. There's not a lot of space, but let's see maybe if we can try to crowd everybody up front. If it doesn't work, maybe we can spell it into the lobby. I don't know. We'll work it out. But if you can give me about 10 minutes or so to get it worked out, we'd like to get a shot for the Twitter feed and the blog. And happy DConf. Thank you.